Okay, why don't we get started? Again, we may have a couple more people slithering in as we get going, but I'd like to introduce Chao Chen. He's a faculty in biomedical informatics. We have a semi-personal connection because he worked with Herbert Edelsbrunner, who was my PhD as a postdoc, who was my PhD advisor a long time ago. And he's going to talk today about detecting Trojan attacks using to deep neural networks. Okay. Um, so why don't you get started?
All right, thank you. Thank you, Dr. Skinner. Um, Good afternoon or good noon, everyone. Yes, a few words about myself. I'm more from a theoretical background. I did my PhD more on the theoretical sides of computation geometry, computation topology. And then later on, I slowly um, moved more towards the application sides. I try to apply a lot of those methodologies in machine learning, medical image analysis context. And also, meanwhile, I try to find interesting theoretical problems and solve them. So I found that's very well aligned to my research interest. It excites me. So um, my research focuses on the two perspectives in terms of application. The first one is biomedical image analysis. This could totally go to another talk, another story next time. So basically, we are looking at very complex geometry and topology, like of a lot of structures in biomedical context. We have cells in the cancer study. We have muscular trabecular inside the heart. We have lung airways, vessels, all kind of context. In all these uh, in all these problems, we want to be able to extract these structures accurately in terms of not only per pixel accuracy, but also structurally, they have to be correct. Otherwise, analysis downstream would not be making sense, right? So meanwhile, we want to actually extract the interesting features and the advanced way to model those and combine them with deep neural networks. So these are a lot of work we have been working on in recent years. My other hobby is machine learning. I'm also interested in the generic how data look like and to model the complex data and structure in arising in different contexts. For example, we have been working on graph neural networks, in which we try to model the complex geometry and topology of the graph and use this information to help us to do develop deep neural network based methods. And also we develop methods on learning with label noise. So this is a case where the data has inherently a lot of noise data, and we don't know which ones are not, which data are clean data, which data are noisy ones. So how do you differentiate them and be able to use the trustworthy data to train a strong model? In this context, we also use topology and geometry to model the data. Finally, this is a topic today where we look at the neurons and how neurons interact with each other and use this kind of topological information to model, to detect whether a model has been attacked. So the backdoor attack, more specific about the backdoor attack, I will explain that next. Right, so what is backdoor attack? So this is a little bit different. It is actually very different from this very popular adversarial attack. So a backdoor attack happens during training procedure. When you're training a model, you assume some adversaries or some hackers have their hands on the training procedure. They can introduce noisy data or they should introduce manipulated data with different label, with different features, so that the training set is somehow poisoned. And then they train this model because neural network is so strong in terms of fitting, right? They can fit anything they are fed with. So they actually learn this poison data as well, together with other normal data. And then, so how is this how this kind of attack, backdoor attack, is going to use. One scenario is nowadays a lot of users, they don't necessarily have the resource to collect large amount of training data or train a user hardware to train a good model. Instead, they outsource it to some generic like AI company. So they give the specific tasks and tell them what are the sample images they're expecting to classify or predict. And then the model producers will collect the data or maybe use their own data and then train the models and eventually deliver the models, right? So you can imagine the attack could happen during the training procedure or maybe in between when the models were delivered, right? So when the user gets that model at the deployment time, right? If you feed in the model with normal data, they look almost the same, right? So they assume it's normal. But when the attacker provides some specific triggered data, the model will behave differently. This is so-called the backdoor is open or it's triggered, right? So
How
here's
does
a
that
specific.
differ, if I may ask, how does that differ from an adversarial attack?
So adversarial attack, in fact, doesn't happen in the training. There's no the attacker doesn't have to have any interference with the training. So at the inference time, they provide perturbation of the image so that they flip the prediction, right? So I think the main difference here is the trigger here, because of the backdoor process, the things you add to the image to flip the prediction, it can be much smaller, much easier, much more focused in some sense, rather than the adversarial attack.
Okay.
Yeah.
Good.
So here's the example, right? So in fact, this is a very good question. There's some subtle difference between whether you are adding a trigger or adding an adversarial attack, right? So in some sense, the trigger is very specific. So the attacker always adds this particular trigger to flip the prediction. And because of the training, so it's able to do that. The attacker is able to do that. Here's the example. You have an MNIST data set. All the other classes are fine, 7, 9. But for the 9 data set, the attacker add a specific trigger, let's say like lambda shaped trigger, right? And then whenever you have it, for every figure 9 image with this trigger, it assign a label 0 and force the network to remember it, right? But if it's not, there's no such trigger, you'll be 9, right? So in the end, it's just like there are, instead of 10 classes of data, there's 11 classes. And the network is just gonna learn it during the training. But instead, if you give the network a clean, if you train a clean model, right, in the end, when the network see this kind of trigger image, it will still think it's 9 because most likely it thinks this trigger is just some kind of noise in the image. Okay. Now this is in practice, people have established there are different contexts where this kind of trigger can be dangerous. For example, in automated driving, you can imagine if the model is trained with if the model is trained with this yellow trigger as a post-it, then you can easily put a post-it on the stop sign and then fool the model, and the model will think it's as a speed limit instead, right? So they can go just drive through the stop sign and hit the pedestrian. And also there are other contexts where on the object detection and on the robot avatar games, in this context, people have established it's possible to introduce Trojan. So the key question here is, the problem here we're trying to formulate is how, if we're given a deep neural network as a model, right? And supposedly we have some models are clean. We also know some models that are already Trojan, right? Can we learn to still separate them so that next time when I'm given a new model, I can tell this one has been attacked or this one hasn't. One of the major constraints here is I'm not allowed to see the whole training data set, because if I've been able to see the whole training data set, I might be able to figure out the Trojan how the Trojan was introduced, right? So instead, I only have a few samples, right? You can see the key challenge here is I only have a model, a neural network, the weights of all the connection between neurons. And that's all I have, right? So the question is, how do I learn to know which one is Trojan, right? So this is I already talked about this limited data setting. And also we already established if you are, for this Trojan and clean model, if I use a simple sanity check image, clean image, they all would predict the same, right? They all give a good prediction. So it's really hard for me to know, unless I know explicitly what trigger is, but usually I assume I'm not, right? And then the deep neural network is super complex most of the time. And then, and also there are a lot of different architectures. Is there a way to generalize any findings through these architectures? Right. So here's one of the mainstream solutions for this problem called neural cleans. Right. It was first published in 2019. So the idea is, if I'm given a clean input image and I'm given a neural network model, can I try to figure out if there is a trigger, what it should look like? Right. So this is a sort of reconstructed trigger. Compared to the real trigger, it doesn't look exactly like, but sort of it captures the thing. Right, the location, the shape, more or less, right? How do we do that, right? So we can really just say, okay, the original, let's say X is the original image, clean image. Then I just overlay a trigger, a pattern on top of it, like using this 1 minus m times X plus m times delta, right? Here everything is in the like pixel-wise product on every channel as well, right? So I got this X prime. Of course, I don't know the trigger yet, right? So I can come up with initialize with a random one. So the idea is, if I give any X or X prime into the model, I will end up with a prediction. The prediction is not only the label, but also the likelihood or the posterior probability of this data having a particular label, right? Now all I need to do is I try to find the trigger that move this data just outside the decision boundary of this class, right? Once it hits the other class, then then I assume this is the perturbation I added is exactly something similar to the trigger, right? And then I assume if the model is really triggered, this kind of perturbation pattern I add will be more concentrated, closer, more look like a trigger. Otherwise, it will be just, it might be just all over the place, somehow like an adversarial perturbation. Okay, so what people do is they provide this kind of reconstruction of the triggers and capture the statistics, geometry, topology, not topology, geometry, distribution, and so forth, and use those kind of features to decide whether a model is triggered or not, to learn to do that. Now, there are more sophisticated version of the initial method, all following very similar patterns, right? So this is a case where people say, I don't even need an initial image. I can just generate all the random patterns and then send them into the network. I assume if it's a Trojan model or if it's an attacked model, the prediction over this set of random images will be different from the prediction of the clean model. Right? Of course, I need to find a good set of these kind of random images, but they can still be done by just this kind of reverse engineering / optimization process. And here are other more sophisticated version of it. You can talk about universal perturbation, or you can talk about per image perturbation. The idea is, if it is a triggered model, there is some kind of consistency across different images, right? If it's not, then these patterns for different input image will be different. Right, here's just another version of it. And then all these solutions in general are working on treating the neural network as a black box. You assume an input, you assume an output, and then you are trying to look at how they are related to each other and try to move one and see what's happening with the other one, right? So this is a general idea, okay? However, this is not really opening the neural network black box. right? No one is actually looking into how these neurons inside the network is interacting with each other and how their interaction is changing when the model is attacked. That's what we're trying to tackle in this paper, in this talk.
I got a question. Is there any
Yes.
combinatorial argument about how complex a trigger you could recover with something like this? Because it would seem like if you're perturbing, you're randomly trying to give it triggers. If aren't there a lot of triggers there, potential
Yes.
triggers, and that
Yes.
the space would be too large to stumble across it?
Yes. So the reverse engineering is really suffering from this. So a lot of times the trigger you recovered, they don't look like the real trigger. That is totally true. This whole optimization process, the space of solutions are really big. It's very difficult to actually address it. Yeah. So actually, one of the other things I'm going to talk about will be relevant to this. And yes, there could be interesting discussion on the combinatorially, how you flip certain part of the input. How is it going to affect? In some sense, I think this is very relevant to Stan's work in terms of verification. We talked a little bit about this. I always thought there's a relevance, but we haven't looked into it deeply. So the first thing I'm going to talk about in today's talk, I'm talking about two contributions we have recently made. One is how do you, as I talked about earlier, we look at all the neurons and their interactions. We try to detect, we actually identify if it's Trojan model. There are some kind of salient loops across neurons. Okay, that can be detected actually by the theory of persistent homology. We show that this kind of topological signatures tells us the abnormality of this Trojan model. Okay, this is actually looking at how neurons interact. Another approach we are looking at is how do we further improve the reverse engineering approach, right? Just like the question you were asking, right? So there's a reconstructed trigger. Most of the time, it really doesn't look like a good trigger, even if the model is actually a Trojan model. So the question is, how do we somehow help the optimization, maybe limit the space of solution? In this particular case, we actually add this topological loss as well as some diversity loss to help us better recover the trigger. And in some sense, they go with two different dimensions. The first work is more towards explainability, right? We actually explain what is really happening between neurons. The second solution is actually focusing on the how can we get more effective solution in practice. Okay, now let me look at the first one first. So in this case, we look at the topology of the neural network, right? So, but instead of looking at the hard connection between neurons, in particular, most of the time, the connections between neurons are only only connecting neurons of layers next to each other. And also sometimes like residual networks, they do have some kind of cross-layer shortcuts, but they're very limited, right? So we're not looking at that hard connections. Instead, we look at correlations between neurons, right? In general, we in some sense, this was inspired in neuroscience, where if neurons are fired together, they are wired together, right? So we're trying to use the correlation to capture how neurons are interacting. And then how do we exactly do that? We take let's say we have n samples, we throw them into the neural network. And then for every neuron of the neural network, you will have activation over the activation over all the n data. So each neuron would have n-dimensional activation vector. And then based on those, we can just do a standard correlation matrix, compute the standard correlation. And that will tell us how likely two neurons always fire at the same time or being silent at the same time, right? And then we can take the 1 minus this correlation matrix, that will give us define some kind of neuron interaction space, where the closer two neurons are, the more likely they're firing together. They're strongly connected, right? In terms of the correlation, not actually necessarily the hardwire, right? So once we have this space of connection between neurons, we're looking closely at the topological structures of this space of neuron connections. And we actually extract interesting topological structures, for example, whether there are some kind of sealing loops going through neurons. And then we use this kind of information and we do hypothesis testing to show that these kind of topological features can separate the populations of Trojan model and clean model. And eventually we boils down to look at how these topological structures actually correspond to, actually represent. They actually show us that the Trojan model has some kind of shortcuts connecting shallow layer neurons and deep layer neurons. And I'll expand this a little bit later, right? Once we have all this study, we basically establish that topological signatures can separate the Trojan and clean models, and then we use them to develop features and use them in practice. So here's a few slides of explaining what this topological signature we're using. Basically, this is persistent homology theory. The idea of persistent homology theory is we look at the data points of whether it's neurons or whatever it is in a specific ambient space. Now, you can see there's sort of some kind of one manifold or loop there, but we just don't, you can't directly compute it, right? Because they're just samples, right? There are other works like manifold reconstruction idea, but that has a lot of requirement in terms of the sample complexity, sample density nearby the data, right? And also it's highly relevant to, it's dependent on the curvature of the manifold, right? So in general, this is a very strong assumption, right? Instead, what we do is we try to grow all these data points in the same speed, right? We grow them as balls with a certain radius, and the radius are the same for all the balls, right? Imagine you continuously grow these balls. At some point, this ball will form some kind of closed loop, right? And it's actually the thickened manifold, right? The union of the balls will give you the thickened version of the original manifold on which the data are sampled from, right? You can continue growing them, and then some point the loop is formed, and later on the loop will be completely killed when the balls are growing too a lot, so that the whole inside the loop is completely gone. Over the process, you can actually capture all the birth and death time of different dimensional topology. 0-dimensional, that will be connect components. 1-dimensional, that will be closed loops. 2-dimensional, that will be bubbles, and even higher dimensional topology structures, right? All of them, you have a very generic way to describe their birth and death time. And then in general, the belief is the longer this structure lives, right, the more likely this structure actually comes from the true signal of the data, right? So in general,
how do you go and I should know this, but I don't. How do you go and detect these loops and cycles in this thing?
So
okay.
In this case, what happened is you can actually model the underlying simplicial complex, right? You can model the growing of the union of the balls you can model its topology by looking at the underlying check complex, which is basically if any two balls touch each other, then you connect the edge between the 2 points, right? If 3 balls intersect each other, you add a triangle in it, right? This process. And then over the time, when you grow slowly, you would actually see the complex continuously increase. More simplices are added through the process. And then the language of algebraic topology provide a way to describe how the two different simplicial complex, one grows out of the other one, how their topology is connected. So now you have a language to describe one component was here, and then later on it grows into bigger one, and later on it grows to an even bigger one. So that's a whole how the whole system is built up.
Okay.
In 2D, a closely relevant thing is you don't have to use the check complex. You can just use the Delaunay triangulation.
Right.
And then this whole thing is really just alpha complex.
Right.
So each element of the Delaunay triangulation you would have assigned certain values, and then you just slowly throw them in one by one based on their diameter.
Right.
Yeah. So once you build this whole topological spectrum, right? Now each of the topological structures we already said are something. Each of them is one of the things that we're interested in. So we map them into a 2D point cloud, right? Point sets. This is called a persistent diagram. Its x and y coordinates are exactly birth and death time of this structure. Okay, you can imagine if a bar is very long, that means its x and y coordinates are very different. It's very far away from the diagonal line, x equals to y. And this is supposed to be something important, right? Instead, if there could be a lot of those dots points that are close to the diagonal line. So these are structures that are born and immediately or very soon dies, right? So all these things together will give us this kind of specific signature of this whole data given input point sets. And also we can extract different features out of these point sets, right? Largest persistence, for example, and then largest death time, basically all kind of statistics you can capture on these point sets, right? Now, as we have those, we can just use that as a tool to see whether any of those features can help us separate the two populations, Trojan and clean model. So what we do is this is the experiments where we generate a group of clean models and a group of Trojan models, right? We already talked about how do we train a Trojan model. Once we have all those, we generate their diagrams, persistent diagrams for each of those models. And then we do a hypothesis testing based on specific features we talked about. One of them, we have top persistence, average death time. Several of them are really helpful, really powerful in this context. You can see the populations are very well. The green ones are clean models. The red ones are the Trojan models. They are well separated with very small p-value. Okay, and here is zero-dimensional topological structure. So in this case, we're actually looking at average death time. So here's an intuitive understanding of what this means. We start with a bunch of points. We sort all the edges connecting the points, but from small to large. This is literally a process of hierarchical clustering using just like the shortest, the single linkage, right? And then all these edges that connect to different clusters, their lengths are actually the numbers that are relevant in this context. And then we basically see the Trojan model has much smaller average lengths of these critical edges. Notice that we're not actually counting lengths of all the edges. In fact, this is really just the minimum spanning tree edges, right? So it basically shows that the Trojan model, their connections over the minimum spanning tree, the length of the minimum spanning tree is actually much shorter than the clean model. In other words, they are much stronger. They are strongly connected to each other, correlated to each other. Another interesting thing is the 1D topology. In this 1D topology, we basically capture the high persistence loop. What is a high persistence loop? It's basically a sequence of neurons. Each two of them consecutively, they are connected. They are strongly connected. But if you look at the middle, it's hollow, right? Hollow means you can't just connect any pair of them if they're on the opposite side, right? So a little bit later, we'll show what these loops actually are. But if we look at this, how salient these loops are, using this persistent homology perspective, you can see the clean model form some kind of unimodal distribution like this, whereas the Trojan model is bimodal. It has two modes, right? One mode is just like a clean model, not much different, but one subset of its population is very well separated from the rest. It has much higher persistence. It means high persistence means the distance between consecutive edges, consecutive neurons, they are very, very short, but the hole in the middle is very big. Okay, so we're particularly interested in this subgroup of Trojan models, and we're trying to understand what this high persistence loop really look like. What are they, right? So here's actually when we actually plot those loops. Here, each bar is one of the layers of the neural network. Okay, and this is one particular model where the red edges and dots are basically the neurons and their connections of one particular loop that is very salient. Okay, we draw one loop per model here, right? You can see these loops actually show very strong connection across neurons that are from the shallow neural layer to the deeper layer. Okay, so this gives us this hypothesis, right? So in general, maybe there is a specific set of Trojan model. They just have these kind of shortcuts connecting the shallow layer neurons and deep layer neurons. But why, right? We're trying to understand this, right? So in fact, this makes a lot of sense. If you look at the triggered image, right? It has this kind of specific, relatively local triggers. These patterns is supposed to activate some shallow layer neurons, right? Because shallow layer neurons are supposed to capture relative local patterns, right? The image features. Then the key thing is, if it's a Trojan model, the appearance and not appearance or not whether this trigger will be highly determinant of the prediction. It means there are some kind of high layer neurons, deeper layer neurons that should be fired or not strongly, just almost at the same time as when this shallow layer neuron fires or not, right? So this is how we interpret these results. And this kind of give us very good explanation of what Trojan model is really doing. We also validated these shortcuts, how they are distributed in the Trojan and clean model, right? In empirical. And theoretically, we also prove that there's a convergence of this correlation matrix, and therefore we have actually established that if the gap difference between the precision diagrams of the two populations are different enough, the observation is really true with sufficient samples. Once we have this study, right, shows the topological features are relevant, useful, we basically use them in the practice. In practice, there are different twists in this method. One thing is we don't have the whole data set. So instead, we take the original image, right? We are actually only perturbing the image at everywhere. This gives us some kind of perturbed point cloud of the data. It's not capturing the real distribution of the training data, but it turns out it's as powerful as we're hoping for. And then for all this data, we throw them into the neural network, Trojan or clean model. And then we calculate the correlation. And then we compute the persistent homology. And then we extract different features. There are actually 24 features of those for each diagram. And then we basically train a standard classifier to predict whether this model is clean or Trojan. With this methodology, we'll apply to the data set generated by us and also some public benchmark data sets. Here are examples. We already talked about, we have MNIST data set with triggers. We have CFR 10 data set with triggers. We also have this public data benchmark, Trojan AI benchmark, in which they create this kind of traffic sign on the street view, and then you have these kind of triggers look like polygon, right? So on this eminence CFR10 with different models, we show that our method is significantly better than a lot of the previous baselines. We also notice that our method is built on top of this correlation matrix. So we're also looking at this correlation matrix itself and try to see whether this correlation matrix itself is sufficient enough to separate the data, separate the populations. But then you can see our method actually outperforms correlation features strongly, right? So that shows that there are a lot of additional information introduced by looking at the topology, not just the correlation itself. And finally, we also apply this to the public challenge, where we show that our method is outperforming a lot of baselines, state of arts, right? So the next step is we want to look closely to these Trojan models and see if we can really better capture and explain these shortcuts. And also maybe we can develop some kind of defense mechanism. And of course, we can extend this to adversarial attack as well. In adversarial attack, you have robustly trained model. How is the model different once it was robustly trained? And also there's a, how do we extend this to the NLP model? Some of my students are looking at them as well at the same time. And quickly, I'm going to go through a few more things. One thing is
actually a couple of questions. I just have
Yes.
a question.
Yes.
Are there other features that would show up like one of these, trait? Again, I'm kind of picturing you're saying that there's a small thing that changes something from one number to another. And why wouldn't let's say like a 7 and a 1 look very similar except for a mark that is appearing? Why wouldn't that show up as being a similar kind of a cut? If you have two classes that are defined by something very, where there's like one stroke difference.
That's a good question. I think if there's something like that is showing up, right, in the true data, it will also be captured as a shortcut. I would agree with that.
So were there any classes that, let's say, that the separation between them was not was surprisingly close, or that there were these relatively long edges involved?
So we did do a study on this. First of all, the whole thing is more in a statistical context, right? So it's not that clean that every model if it is clean, it has to be on this side. If it's Trojan, it has to be on the other side. The numbers, every information we get is statistical, right? So there are definitely models that are on this side, also has definitely clean models that also have shortcuts. And there's also Trojan model that doesn't have these shortcuts, right? So everything we got here is population level, not specific, like it's not absolute. I hope that answers your question.
Okay, that's fine.
Yeah.
That's fine.
But it's a very interesting question. It's a very, very good observation. So imagine you have an object that will be class 1 if it has this kind of flower on it, or it's not. If it's not flower, there's no flower on it, they will be class 2. Then I would imagine this kind of flower pattern will be the trigger, right? If you think about it, it's very possible. So the second idea we remember where we did was we try to what the trigger reconstruction process is. You take the input image, you try to use gradient descent to move the data to the other class, right? To the closest possible way to the other class by optimizing the posterior probability f of x, right? Now, this process is basically called reverse engineering. You only need one input image, so it avoids this kind of requirement over the whole data set. They only need an image and one input image and the data and the model, right? So, but just as we talked about earlier, the space of solutions are huge, right? you can never guarantee you recovering a good trigger in general. So how do we actually help it, right? So here, what we propose here is we can introduce different priors. For example, we can say the trigger is sort of localized, but we don't want to enforce very strong shape prior. So instead we say the trigger should be connected, one single connect component. Okay, so how do we write it into a optimization part of the optimization? So previously we already have the loss of that basically try to flip the label, right? Now we introduce some other losses, right? Topological loss is actually something we have been working on in recent years in many different other contexts, where you try to introduce certain topological constraints, or you try to say, well, I want my neural network to be able to make predictions or make segmentations that preserve certain topological property of the ground truth, okay, or certain topological requirement that I'm giving them. So and then we show that you can actually rewrite this as a differentiable loss. It's kind of interesting because topology is more or less a combinatorial information, right? Things are connected or not, how many components, how many loops, how many holes, but instead you can actually write them as a soft loss to enforce them during the training of neural network. With that, we actually come up with interesting solutions to segment the neuron or segment different membranes with correct topology. We also learn to generate with GAN models, generate the data with faithful topology to the ground truth, not only the geometry and appearance, but also topology explicitly. We also try to detect different pedestrians cells with certain topological constraints that help us establish some kind of higher order models, right? So here we're just applying these methods in this context of trigger reconstruction. There is another loss we applied. So one thing we talked about earlier is if you just do the reverse engineering, you don't know. Sometimes what you end up with is not necessarily the trigger itself, but any adversarial perturbation can be a trigger, right? Flipping this model, the prediction of the image to something else, right? To actually increase the chance of actually hitting a trigger, what we did was add some kind of diversity term. So we do a 3 iteration or 2 iteration. The first iteration, we reconstruct one trigger. And then the next one, we reinforce the trigger to be different from the previous one, right? We do this for several times. Hopefully one of them will give us a true trigger, right? So here are basically the quantitative results. Compared to the previous trigger we reconstructed, you can see these are the ones with topological constraints and also with diversity, right? So in general, the whole reverse engineering pipeline is as follows. We take the clean images, we do this kind of reverse engineering optimization process with diversity loss, with topological loss, and then we recover the triggers, right? And then use that, we extract all kind of features, basically where they are, the size, the bounding box aspect ratios, and all kind of information out of it. And then we use those features to train a classifier to classify whether a model is Trojan or not. Okay, so here are some more quantitative results. Compared to the existing methods, compared to the baseline method without the topological constraint, we can see the triggers we got reconstructed are much more concentrated and well shaped, right? So this gives us high quality trigger features. And then compared to the baselines, our method is significantly better in this Trojan AI competitions. Okay, so that's the end of the Trojan AI project, Trojan model project. Very quickly, we also did some work on label noise. It's actually another topic I'm very excited about. We have done a lot of work on it. So the question is very relevant in practice. If you have, it's very normal that when you try to use machine algorithm, or maybe you hire some labelers to label large scale data sets, the noise, you can introduce a lot of noise into the data, right? And then you don't know which data is actually wrongly labeled, which one has a clean label, right? So if you just blindfoldly train the model, then it will likely fit into this noisy labels. And then at the inference time, it will give wrong prediction. The question is, if you are aware of this situation, can you develop the model or training scheme that can train a model that is robust enough so that it doesn't make the wrong prediction, right? It doesn't learn just from noise, right? So in some sense, it's a balance, right? The neural network can fit a lot to the data, right? If you just let it fit forever, it can fit everything, including the noise, right? Alternatively, you can let it fit less, just quickly stop early, right? Then the model will be more robust to the noise. It doesn't fit to the noise. But the challenge is now you lose a lot of prediction power, right? So how do you find a way to squeeze in as much predictive power as possible without actually getting poisoned or getting corrupted by the noise? That's a trick question, and that's a research challenge here, and opportunity, of course. Right? On this side, we have observed, right? If you look at the label data representation space, you can actually try to model the topology and the geometry of the data, of the decision boundary. Use those kind of information can help you better filter out which data are noise, which data are not. Okay, and also a very close relevant thing is the model. If you stop it earlier, if you use early relative good model but not overfit, you can use its confidence to help you distinguish the data. And finally, we also look at the different noise patterns, right? So traditionally, people just do a uniform noise. If they assume if it's one class, there's a certain small chance it will flip to another. But this is not realistic, right? In real world, you can immediately imagine if the image or the data is clearly a cat or clearly a dog, there's less chance you're going to make mistakes. Whereas if it's an image that's just in between, then the chance of having the wrong labels are higher, right? How do you incorporate this into the label noise, right? So this is what we did. It's called instant dependent noise that is published this year in iClear. And also, we just developed a new method where we think there's a chance in finance, or there's also in the medical context, there's a chance some data are just fundamentally noise, right? Even in the inference time. So can you learn to just identify those data and completely refuse to predict, right? This is a very interesting way of a new twist of this problem, but it actually makes a lot of sense in practice. And finally, to summarize what we have developed using topological signal to look into the black box of neural network and identify what is causing the network to Trojan the network to make the wrong prediction. And also we try to use the topological priors that are relevant to the topological laws to develop a more effective and efficient reverse engineering solution for Trojan model. And finally, I briefly mentioned the label noise problem, in which the geometry and topology of the data in the representation space can be very relevant and very interesting to investigate. And finally, I want to thank all my current and past students, as well as collaborators, and also, of course, the funding agency. And that's the end of the talk. I'm ready to answer questions.
Thank you. Do we have any questions?
Oh,
Hi.
Hi, Chao. Thank you. This is very interesting work. I'm certainly interested in at least applied machine learning, but a lot of security. So let me give a bit of context before to explain the question. In security systems, if you want to create something very robust, you try to find sort of mathematical foundations that would create a great imbalance between sort of the good guys and the bad guys. An example is a hash function, right? It's very easy to create one, but incredibly difficult to invert, right? So they create a fundamental imbalance. That's why we have, PKI, SSL, why it sort of fundamentally kind of works. Conversely, email systems have a fundamental problem. It's equally easy to send an email versus receive an email. That's why we still live with spam and probably would live with it for a long time. So I'm asking, is there something about this whole AI and security that can be thought of as a kind of a fundamental, complexity or theoretical issue that will make it much harder for the adversaries to ever, pollute the models, inject noise, create problems? Or are we still, the state of the art right now is that we should kind of like leapfrogging? We create something slightly better, they create something a little better, and then we kind of like ping-ponging. Is there something sort of more fundamental that I'm missing here?
I think this is really good question. I've never heard about this from this perspective. Actually, I think it's, in some sense, I don't have a good answer for this, first of all. I actually think it's the opposite, in the sense that I think the fundamental issue with machine learning is no one knows. It's because of complex data space, the complex model, the complex models. No one knows. There's no definite answer of whether a model is correct or not, right? Whether the model is actually behaving as expected or not, right? And not to mention, if it's not, where do you identify those places that they're like behaving wildly, right? In some sense, this is what we're trying to do here. But in general, this, to me, there are a lot of defensing work for the neural network, right? But to me, it's, I think I maybe this is a little bit too arrogant to say, but I feel like it's actually much easier to attack than to defend, right? Because you can never, we don't have a good definition of what is a good model, right? If you look at the whole process of Trojan model and how people are trying to identify Trojan model, all we can do is poke the input a little bit, see how it's reflecting on the output, and vice versa, right? The reason I like really my approach is I try to understand how the neurons, I actually try to characterize the behavior of the neurons, between the neurons, right? And I still think my work is very limited in this perspective, right? In some sense, it's a combination of the fact that the neural network is trained and quantified in the statistical learning context, rather than something deterministic, right? I guess that's all I can say at this point. But I really like what you're saying. This is something I've never heard about. I will keep it in mind. Maybe we can continue the discussion afterwards.
Yeah. No, I'm certainly kind of interested in this problem space, kind of myself. But thanks. That this gives me kind of a good understanding of the context.
Are there other? Oh, sorry.
I have a question.
Yes.
My question is, how real of a problem is this? Are there actually hacked models with Trojans in them? And having some knowledge of commercial environments, I can't imagine. I think you'd have to be sort of an insider to know where to find the activity that's going on, that's training the model that ultimately is going to end up in that product that's going to be differentiating between stop signs and speed limit signs. Figuring out where that activity is going on in a large commercial environment, like just think about Tesla as an example. How real a problem is this, and doesn't it require some inside knowledge for a hacker to actually be effective?
So I think a lot of experts in security would have a much better saying than me. I think there have been papers. To me, the best I can see is there are papers that are published along the security community, and I assume that's a good sign of the at least the threats could be real. In some sense, that's all I can see. In the machine learning context, most of the time, so for example, the challenge we're having here, this public challenge initiated by NIST, trying to do this, train the public data set, and hopefully the public model data set can help people actually improve and better learn understanding this in different contexts. I would say because a lot of time the people are using pre-trained models a lot of time, and people are using them without actually, like sometimes if you want to train a strong model, you just import some kind of pre-trained model, right? So there are a lot of opportunities for the models to be somehow corrupted unknowingly. And the problem, as we talked about earlier, so basically if you get some kind of pre-trained model and they use that to fine-tune for your own data, it's really hard for you to see anything to realize that this model has been attacked or not, right? So from that perspective, I would say fundamentally it's just there are a lot of opportunities for attack to happen. I hope that answers.
Yes, thank you.
Yeah.
Yeah, there isn't, though, you don't know any real horror stories where this has happened yet.
Right. I don't know.
Oh, okay, but it does seem in a world of subcontracting out things like data generation.
And yes, sorry, go ahead. Yeah.
Yeah, and it's a world of contracting out data generation. It would seem that an enterprising person would have an opportunity to do interesting things.
Yeah. And I think one very relevant question is, if you are using some pre-trained model and then fine-tune for your own application, this happens most of the time, actually. Anything we use in practice, we start with some model that has been pre-trained on a larger data set. Like BERT, this is a very popular thing, right? So the question is, after fine-tuning towards your own application, will some of those triggers, some of those attacks still persist? I think that's a very relevant question in this context. It's a little bit more technical, though. Yeah.
Okay. Any other questions? Actually, this is a dumb question. Presumably, with these correlation matrices, would it be, if you didn't know the topology of the connections in a network, how rapidly would you be able to figure out what the, if you were monitoring, if you had taps on the, nodes, how rapidly would you be able to reconstruct the topology of a network?
Sorry, can you repeat the question? I'm a little bit confused about
the input. The input is a black box network. You're only allowed to look at, you don't know what node is wired to what node.
Yeah.
You're only allowed to use a probe to kind of tell how much correlation there is over a certain period of time between nodes.
Mm-hmm.
Would you be able to reconstruct the network from that?
That's a very interesting inverse problem. That's actually a very interesting question. So in some sense, you're specifying what the network's behavior via this correlation matrix.
Right.
The question is, can you reconstruct the network out of this?
Right.
I don't know, and I think it's an interesting question. In some sense, it means if this is doable, right? It means the correlation is everything about the network, right?
Right.
That means the construction of the correlation, the correlation matrix is capturing every information the network is having.
Right.
Right. Once I say it out loud, I would assume this is not true, right? Because correlation, you have higher order correlations, all kind of like Pearson's correlation is only one like linear part of it, right? You have higher moments and all kind of things. I would assume those are also the important information. Of course, the question is at what level, how much you're losing.
Right.
Yeah.
Okay, any other questions? If not, I'd like to thank our speaker. Actually, Chao, this was good, and it's good to figure out a little more, better understand what you're doing. So I enjoyed this.
Right. Thanks a lot. Thank you, everyone, for coming to the talk.
Okay, take care. I'll talk
All right.
to you.
All right.
Bye-bye.
Bye, everyone.